Welcome to lesson 1.1, example 2, being able to apply facts about points, lines, and planes. Defined terms in geometry are defined based on some of the undefined terms. Again, our undefined terms, because they have no definite size, are point, line, and plane. So we define the following things, which you've learned about previously in middle school: segments, endpoints, rays, opposite rays. All of these are based on our three undefined terms. So assuming that we all agree what a point is, a line is, and a plane is, we can move forward in defining some of the other terms and looking at how to name them. A segment is a part of a line between 2 points. So I have 2 points, and we know that it takes 2 points to make a line. We'll call this one C and this D. C and D may be on line L. But I'm not interested in the fact that they're on line L so much as I'm interested in the segment CD, which has 2 points. Either one could be the start point, and the other one the end point, and I could go the other way as well. So it is a piece of a line, and it's actually measurable. We could take a ruler and we could measure the distance between point C and point D. Now CD segments have notation, just like lines have a notation. If we're referring to the name, okay, we just call it CD, and we put a bar over it without arrows. The arrows would indicate that we're talking about the line CD. The bar indicates that we're talking about the segment CD. So paying attention to notation is important as we go through this. And the only other thing that I'll say about this, because we're going to get to it, is that if I'm talking about the distance between C and D, we actually would do it without a bar, okay? So here we're saying, hey, look at that line segment, its name is CD. We're talking about the line segment. Here, if it doesn't have a bar, then I'm actually referencing its distance. So if this were 3 units long, I would say the distance from C to D is 3 units long. So this represents the distance from C to D. So a couple things right now. We have lines which have an arrow hat on top, a line on top of the letters, line segments which just have a bar on top, and then the distance of a line segment, the distance from a point to another point, which has no bar on top. An endpoint, well, it seems kind of silly to define a segment before we define an endpoint. An endpoint is one end of a segment or a starting point of a ray. It could be considered a starting point. So if I'm starting at C, even though I'm starting there, it's called an endpoint. So C and D are endpoints. A ray is part of a line. So again, we could have this imaginary line in space connecting infinitely many points that are on the line. And however, if we're talking about a ray, we're talking about it starting at a particular point, so a particular endpoint, and extending in one direction forever, not going both ways like the line does. It does take 2 points to name a ray, and they have to be in a specific order. The order is that it has to start with the first endpoint has to be the start point. So if I have this as, it doesn't matter whether it's alphabetical or not, I'm going to do it intentionally wrong. This is R and this is K. And most people would say, well, let's just do it alphabetical, it'd be KR. But it isn't KR. It starts at R. So it has to be named the ray RK with a little arrow. And it doesn't matter if I had a ray going in another direction. Maybe it went to the left. We'll call this ray Now, let's take a look. If you're reading left to right, you're like, oh, that's ray AZ, but that would be incorrect. We have to start here. This is the ray ZA. That notation indicates that it starts at Z and passes through A. Starting at Z, passing through A. This one, starting at R, passing through K. And the notation for this, the symbolic notation, is the 2 points, a point that's on the ray and the end point or start point, with a ray above them. And then we have one last definition for this section. Opposite rays are two rays with a common endpoint that form a line. So I have this ray, AT, and this ray, AC, not CA, but AC, and those two together are opposite rays. Basically, when you put them together, they would form a line. They share a common endpoint, that endpoint being A, or a common start point rather, common start point, and they go in opposite directions to form a line. So we're going to go through some of these example problems where we're drawing figures. We have to draw, label, and name each of the following. A segment with endpoints U and V. So I'm going to draw it, and it doesn't matter which order you have it in, U and V. This is segment UV. Its distance, if we had a ruler to hold up to, or tick marks, we would say that the distance from U to V is 1, 2, 3 units. But right now we weren't asked for that. We were only asked to draw it, label it, and name it. There's the naming it. So when you see this on the test, don't say, oh, that's a segment. That's not naming it. That's identifying it as a segment. When we're naming it, we actually use the letters and the correct symbolic notation. Letter B, array with endpoint T. So this is the start point that passes through P. So our ray has to go through P. And I'm going to put T here just for fun, even though most of you like to go left to right. We're supposed to start at the endpoint T and pass through P. And this would be ray TP, using capital letters and the hat, the correct notation above it. Opposite rays with endpoint Q. Well, you'll need to name some other points, so maybe you have R and maybe you have S. And one of them goes one direction and the other one goes in the complete opposite direction. So those are opposite rays. QR and QS are opposite rays. Letter D, a ray with endpoint P passing through T. So I have P and I have T. This time I will go left to right. Endpoint being P, passing through and extending beyond T. That's the ray PT. And letter E, drawing three non-collinear points J, K, M, and then draw the line containing the draw the plane containing the 3 points. So here's J and M. It doesn't matter, or J and K. It doesn't matter where I put them. This is no joke. They are going to be on the same line. Any 2 points define a line. But as long as I make sure that M is not on the same line as J and K, then I have 3 non-collinear points. And now, connecting them, I form a 2-dimensional space, in this case a triangle. And since it has an area, we would call this plane JKM. And even though our triangle is bounded by those lines, this plane actually extends forever in all directions. In the directions, it extends beyond those lines. All right, so we're going to talk a little bit about postulates and intersections. I'm going to have you try a couple things when we get back to class. But here we go. Think about it. Are rays from B and D the same? Are the rays from B and D the same? Here's B, here's D. They are not, even though I put them like this. Wow, and I didn't even plan that. One of them starts at P and passes through T, the other one starts at T. So the answer is no, they have different starting points. In E, does it matter which letter which order the letters are for the plane? Actually, no. I could have named it plane MJK, as long as they're not in collinear. So if you try to name a plane and you use points that are on the same line, that would be bad because you don't have a two-dimensional space. You have to make sure you use 3 points that are not on the same line. They have to be non-collinear. Letter C, if PQ and PQ and RS are names for the same line, what do we know about the points P, Q, R, and S? Well, if those are the same line, then those points have to be collinear. All right, so I want you to think about this a little bit. This is going to be pretty much common sense to you, but you will have to be familiar with and be able to identify these postulates, and if they're written correctly, they're Euclid's initial postulates, the foundation for the rest of his geometry, on which we built triangles and facts about triangles. And the cool thing is that works when we're talking about a plane being flat or a line being a straight path, which is how Euclid's geometry is defined, because back then they thought the Earth was flat. Well, if you look at how we work in space or how things travel in space, though, if you pull back on a larger scale above Earth, or pull out from Earth a little bit, a line can actually be a curve, in which case it would intersect at more than one point. And that type of geometry is called hyperbolic geometry. We're not studying that, though, that's later. Right now we're just studying the foundations of geometry, Euclid's geometry. So through any blank points there is exactly blank line. How do we get a line? Well, you already know this, we've been doing it for a while. You have to have at least 2 points to make one line. Postulate 112, we don't memorize them by the name. Most of our postulates will have names that correspond to the geometric shape. Through exactly blank non-collinear points, there is exactly one plane containing them. Well, how many points does it take to make a plane? Well, if I have 2, that's a line, so I need 3, and they do have to be non-collinear. That's a key vocabulary word. Because if they're non-collinear, then it makes a two-dimensional surface. If blank points lie in a plane, then the blank containing those points lies in the plane. If 2 points lie in a plane, then the blank containing them, the line containing those points, is also in the plane. This is it for example 2.